Hello all. In this video we will be using the properties of the projection operation which we derived in the earlier video in order to obtain the oracle complexity bounds for the projected gradient descent for smooth functions. So we will begin with the smooth and convex case. The metric for this case will be, as usual, the optimality gap at xt, which is given by f of xt minus f of x star. So for L smooth and convex functions, the oracle complexity required to make sure that the optimality gap is less than epsilon is given by t is equal to order of LB by epsilon with step size eta equal to 1 over L. Observe that this result is exactly the same as what we obtained in the case of unconstrained gradient descent. To derive this result also, we will use exactly the same outline as we used for gradient descent. Of course, however, the co-coercivity property does not hold for the gradient map, and instead we have to use another alternative property that would not be as general but would hold only at xt. We will basically be using the compact form of the updates given by xt plus 1 equal to xt minus eta times g eta of xt, where recall that g eta of xt is the gradient map. Step 1 is the non-increasing function property that can be derived from the smoothness of f. So from the quadratic upper bound condition, we have that f of xt plus 1 less than equal to f of xt plus inner product of gradient f of xt with xt plus 1 minus xt plus L by 2 norm square of xt plus 1 minus xt. From the definition of g eta, xt plus 1 minus xt is minus eta times g eta. So therefore, substituting this definition, we get that the left hand side is equal to f of xt minus eta inner product gradient f of xt with g eta of xt plus eta square L by 2 norm square of g eta of xt. Now in the last video we have seen the descent property, which said that inner product of gradient f of x with g eta of x is greater than equal to norm square of g eta of x. So using that property here, we get that f of xt plus 1 is less than equal to f of xt minus eta square 1 by eta minus L by 2 norm square of g eta of xt. So in case eta is less than 2 by L, it follows that f of xt is a non-increasing sequence. Next, let us derive the alternative condition to co-coercivity. For that, we write down the two properties of interest, namely the quadratic upper bound, which is that f of xt plus 1 is less than equal to f of xt inner product with gradient f of xt plus 1 minus xt plus L by 2 norm square of xt plus 1 minus xt, and the convexity condition, which is that f of xt minus f of x star is less than equal to inner product of gradient f of xt minus x star. And adding these two together, we get f of xt plus 1 minus f of x star is less than equal to inner product gradient f of xt minus x star plus inner product gradient f of xt plus 1 minus xt plus eta square by 2 norm square of g eta of xt. Now we can cancel the terms within the inner products, and therefore the final bound becomes f of xt plus 1 minus f of x star less than equal to inner product of gradient f of xt plus 1 minus x star plus eta square by 2 into L norm square of g eta of xt. So let us keep this inequality for now. We are not there yet. Now we need to bound the first term in this inequality on the right. For that, let us again use the angle property of the projection, which said that x minus px of x inner product with z minus px of x is less than equal to 0 for all z in calligraphic x. Now we replace x with xt minus eta gradient of f of xt, so that px of x will be replaced with xt plus 1. Also replace z with x star, so we get inner product of g eta of xt minus gradient f of xt, x star minus xt plus 1 is less than equal to 0. This implies that we have the bound inner product of gradient f of xt plus 1 minus x star is less than equal to inner product of g eta of xt comma xt minus eta g eta of xt minus x star. So we can expand this inner product and write it as less than equal to inner product of g eta of xt minus x star minus eta times norm square of g eta of xt. Substituting this in the inequality that we earlier had, we can get the required alternative to co-coercivity, which is that f of x star minus f of xt plus 1 plus inner product of g eta of xt minus x star greater than equal to eta square 1 by eta minus L by 2 norm square of g eta of xt. Let us come to step 3. The rest of the proof is in fact the same way as the unconstrained gradient descent. We can write down the update equation and take norm square so as to get xt plus 1 minus x star norm square equal to xt minus x star norm square minus 2 eta inner product of g eta of xt minus x star plus eta square norm square of g eta of xt. And then use the derived alternative to co-coercivity condition so as to get that the right hand side is less than equal to xt minus x star norm square minus 2 eta optimality gap at xt plus 1 f of xt plus 1 minus f of x star minus eta square 1 minus eta L norm square of g eta of xt. Again, if we assume that eta is less than 1 by L, then the last term is negative and can be dropped. So we are left with xt plus 1 minus x star norm square less than equal to norm square of xt minus x star minus 2 eta f of xt plus 1 minus f of x star. So this is the required one-step inequality. In fact, you can compare this with the gradient descent where we had a similar inequality except that f of xt plus 1 was replaced with f of xt. And you will see that that will not make much of a difference. Then taking telescopic sum, we have that summation over t from 1 to capital T, f of xt plus 1 minus f of x star is less than equal to 1 by 2 eta norm square x1 minus x star minus norm square xt plus 1 minus x star. The negative term can be dropped so that this is less than equal to 1 by 2 eta norm square of x1 minus x star, which is bounded by b over 2 eta, where b was the initial square distance from the optimum. We have already proved that the sequence f of xt is non-increasing, so that the bound on the optimality gap is given by f of x capital T plus 1 minus f of x star less than equal to 1 over t summation from t equal to 1 to capital T f of xt plus 1 minus f of x star less than equal to b by 2 eta t. Now we need to choose eta as large as possible in order to make this bound as small as possible. So we will choose eta as 1 over L. So therefore the bound becomes LB by 2 eta. And therefore equating it to epsilon, we get the required oracle complexity bound as t is equal to order of LB by epsilon. Before concluding, a remark. You can actually get this result in fewer number of steps, but here I have deliberately used many more steps because I wanted the structure of the proof to be same as that of the gradient descent in the unconstrained case. One big advantage of this proof style is that we would not have to modify it much for the strongly convex case. In fact, the similar structure will work there as well. Coming to the smooth and strongly convex case, we have the following result. Under the assumptions that f is L smooth and mu strongly convex, the oracle complexity to ensure that the square distance from the optimum xt plus 1 minus x star norm square is less than epsilon is given by t equal to order kappa log b by epsilon. For the choice, eta equal to 1 over L. Again, the result is similar to what we had in the gradient descent case. This is remarkable because even though geometrically the constraint problem looks to be difficult because the iterate is not allowed to move along the direction of the steepest descent, but instead it has to move in some other direction. However, for both cases, we are seeing that the oracle complexity bounds are the same. This also suggests that projected gradient descent as a method is not bad because it is performing at par with the unconstrained gradient descent without any loss of optimality despite the presence of this calligraphic X. So later we will see that any enhancements made to the gradient descent will also carry over to the projected gradient descent. We begin our proof by deriving the alternative extended co-coercivity condition for the strongly convex case. So as in the convex case, we write down the two properties of interest. Quadratic upper bound, which is that f of xt plus 1 less than equal to f of xt plus inner product gradient f of xt plus 1 minus xt plus L by 2 norm square of xt plus 1 minus xt. And the quadratic lower bound, which is that f of xt minus f of x star less than equal to inner product gradient f of xt, comma xt minus x star minus mu by 2 norm square of xt minus x star. Adding them together, we get f of xt plus 1 minus f of x star less than equal to gradient f of xt plus 1 minus x star plus eta square L by 2 norm square of g eta of xt minus mu by 2 xt minus x star norm square. The second part is the same, and we bound the first term as gradient f of xt plus 1 minus x star less than equal to g eta of xt minus x star minus eta norm square of g eta of xt. So as to get f of x star minus f of xt plus 1 plus inner product g eta of xt minus x star greater than equal to eta square times 1 by eta minus L by 2 norm square of g eta of xt plus mu by 2 xt minus x star norm square. So this is our alternative to co-coercivity for strongly convex case. Next we use the update equation as usual by taking norm square and expanding as xt plus 1 minus x star norm square less than equal to xt minus x star norm square minus 2 eta inner product of g eta xt comma xt minus x star plus eta square norm square of g eta of xt. Substituting the second term from the alternative to co-coercivity property, we obtain xt plus 1 minus x star norm square less than equal to 1 minus mu eta xt minus x star norm square minus 2 eta f of xt plus 1 minus f of x star minus eta square 1 minus eta L g eta of xt norm square. Here, assuming that eta is less than 1 over L, we can drop the last term as usual. Now there is a slight departure from the proof that we had for the unconstrained case because we are still left with the optimality gap term on the right, and therefore this is not really a contraction bound. So we need to eliminate the second term as well in order to establish the contraction bound. The final contraction bound will be obtained by bounding the optimality gap, which is the second term here, in terms of the distance from the optimum. So f of xt plus 1 minus f of x star is greater than equal to gradient of f of x star, comma xt plus 1 minus x star plus mu by 2 norm square of xt plus 1 minus x star. And here the first term on the right is greater than equal to 0. So we get greater than equal to mu by 2 norm square of xt plus 1 minus x star. So we have used the optimality condition in order to conclude that gradient f of x star inner product with xt plus 1 minus x star is greater than equal to 0. Adding this to the earlier obtained bound, we obtain that xt plus 1 minus x star norm square less than equal to 1 minus mu eta xt minus x star norm square minus mu eta norm square of xt plus 1 minus x star. Instead of dropping the last term because it is negative, we take this on the left and rearrange in order to get xt plus 1 minus x star norm square less than equal to 1 minus mu eta by 1 plus mu eta norm square of xt minus x star. So if we can set eta equal to 1 over L to ensure the maximum possible contraction, then applying this bound recursively and recalling the definition of B, which was the initial square distance from the optimum, we obtain that this is less than equal to L minus mu by L plus mu whole raised to the power T times capital B. So as earlier, the distance from the optimum decays exponentially with T. The oracle complexity can again be obtained in the same way. We set the right hand side equal to epsilon and recall that kappa is equal to L by mu, which is much greater than equal to 1. We obtain T equal to order of kappa log B by epsilon. Finally, we come to the general smooth, possibly non-convex case. That is, we allow f to be arbitrary smooth function, but we still require calligraphic x to be closed and convex. Now in this case, it should be clear that we cannot use gradient norm as a metric because gradient norm does not go to 0. Instead, as you might have guessed, we will have to use the gradient map norm as a metric, which does indeed go to 0 at the optimum. Under the condition that f is L smooth, the number of oracle calls required to achieve min over t from 1 to capital T, norm of g eta of x less than equal to epsilon is given by t equal to order of LBF by epsilon square. Recall that BF was the initial optimality gap for eta equal to 1 over L. The proof for this case is very simple. In fact, we have already established the non-increasing function value. So we have already established that f of xt plus 1 is less than or equal to f of xt minus eta by 2 norm square of g eta of xt when eta is less than 1 by L. So all we need to do is to carry out the telescopic sum on this inequality so as to get the bound minimum over t between 1 to capital T norm square of g eta of xt less than equal to 2 by eta t f of x1 minus f of xt plus 1, which is less than equal to 2 by eta t f of x1 minus f of x star, which is less than equal to 2 bf by eta capital T. So this is the required bound. We can set eta equal to 1 by L to minimize this bound, and then taking square root on both sides and equating to epsilon, we will get the required result that t is equal to order LBF by epsilon square. In summary, we have analyzed the three cases for projected gradient descent, and in this case we don't even need to draw the table because we have the exact same result as the gradient descent for convex, strongly convex and non-convex cases. So in the end, the projected gradient descent did not pose any problems for us. Although we had to see many properties, overall it turns out that we did not need any special conditions on calligraphic x except for convexity and closeness. So that is all for this video. We will start looking at projection free methods in the next video.